Hi there, welcome back here, guys. In last lecture, we have been talking about the blocks in the blockchain, specifically how they are linked together. So when you will invalidate one block, all of the following blocks are invalid as well. In this lecture, we'll be again working on additional information lecture. It will be optional one, but quite important one, and maybe it will be quite also longer than other lectures. So in this lecture, I would like to explain you how the bytecode works, how the instructions in the bytecode are executed. So we'll be talking about this part here. Okay, so if you already know how bytecode works, go ahead, you can skip to the next lecture. Okay, guys, so for those ones that staying here with me, we can inspect this bytecode, but first we need to understand how the bytecode will be, or what part of the bytecode is deployed to the Ethereum network. Okay, so first let's inspect the transaction which was responsible for deployment of our bytecode, of our smart contract of Faucet. Let's inspect your transactions in this menu, and we have quite a lot of transactions now because we have been remigrating. But what we are looking for is the last contract creation. This should be our faucet. Okay, so when I will click at this, I can see part of the data of the smart contract that has been deployed. Okay, actually, this is not a part of what has been deployed to the network, but it is the entire smart contract. Okay, so in the transaction data of the transaction, which was responsible for deployment, we have an entire bytecode of smart contract. Let's copy it. Let's go to calling editor and let's verify it. Let's go to build contracts, faucet.json, and let's search here. And you will see this entire smart contract is here, the bytecode of our entire smart contract. Okay, that's the entire smart contract. And now let's search here for deployed bytecode. So deployed bytecode should be this, what is after the transaction on the blockchain. Okay, so when I will go to Ganache and I will search here for a contract and I will search here for my faucet smart contract, here should be bytecode that has been deployed. So this second part of the bytecode. Unfortunately, here I don't have information about the bytecode, but I can make a transaction to the network and I can ask for a code. You can do it like this. Let's go to terminal and let's run here Truffle console, and we can make here a transaction with the call of web3, so web3.eth get code, and you'll provide address of your smart contract here. So go back to Ganache and let's copy here address of this smart contract. Let's paste it here and let's get here. Here's a bytecode that is deployed to network. Okay, so now when I will copy this, let's copy this smart contract. Let's go here and I will search here for this. You will see this is the entire deployed bytecode. Okay, in the deployed bytecode field here, and this is the second part of the bytecode of the entire bytecode. So that's this part here, what we are deploying. Okay, so now we can differentiate between what we are sending in a transaction. In a transaction, we are sending entire bytecode, but on the blockchain, we don't need to deploy the entire bytecode. We just need to deploy the execution part of the bytecode, so the functions and stuff. And this part here, what's basically it's saying, this first part, oops, I copy here something. Okay, this first part here, what's basically saying is there's an initialization part of the code, which should be run before we'll deploy it on the network. Okay, and what I would like to inspect is what these instructions do. Okay, so I would like to know what these instructions do in this initialization phase. I need to warn you, this will be quite complicated and it can be overwhelming from the start. It's not important that you will understand everything in the details. The important here to understand is a big picture of this. How does it work? How it works. Okay, so what we are going to do, we'll copy this instruction. So the code that is run when we are sending transactions to this first part of the bytecode, this should be this, what we are not deploying. So this here, starting with the FE, or starting with the 60 and ending with the FE. Okay, so let's copy this and let's paste it into some file when we'll be writing some nodes. So I have here already nodes.txt. You can also create the one if you don't have it, nodes.txt or any file. It can be any file, and let's paste it here. So that's the instructions of the initialization of the bytecode. Okay, I need to introduce you with some couple of things before we will get any further. Okay, so this is the instruction. I will mark it as 0x, so we know that's a hexadecimal 0x, and the instruction of the initialization phase of the bytecode. Okay, I need to go here to Carbo. Here is an image of a node, of the client in a node on a computer, where we have also Ethereum virtual machine. As I was mentioning before, Ethereum virtual machine is responsible for execution of the bytecode. So when the node will get a transaction and will execute it, the bytecode will go into EVM and it's executed. Okay? This initialization code will be executed into EVM. So I'll mark it here. This bytecode will be executed. Okay, the bytecode will be executed. Bytecode. Okay, so other part here of this problematic or problematic of this topic is the type of the storages the EVM has accessible. EVM has accessible three types of the places where it can store a data. It can store a data into the storage. Then it can store a data into memory, and it can store a data into stack. Storage is used for a persistent data. So when you will do any changes in a transaction and you will store the data in a storage, this will be persistent. So next call to the smart contract, you will retrieve the data back. So you can have this persistent storage. The memory, you are storing some you are computing some stuff and you're storing it to memory. After the smart contract is done with the execution, the memory is wiped out. Okay, so this is a basically persistent storage. Memory is wiped out whenever the execution is stopped. The stack is a special kind of the storage which is responsible for providing a data from the instructions of the bytecode. Okay, so this will be talking about mainly here about the stack. The memory is just is a temporary storage. When you're executing some function, for example, you're storing some what you're computing, you're storing there, but after the function is done, the data are wiped out, or after a smart contract is done, the memory is wiped out. Storage will be persistent. Okay, so let's talk about the stack. So instructions from a bytecode are stored into the stack. Okay, you can imagine stack as a structure where you're getting hexadecimal basically instructions from the bytecode. So for example, from a bytecode, you will get the first instruction, let's say 0x fa, you will get the instruction 0x3, 0, and so on. So you will be storing this data from the instructions from a bytecode into the stack, and you will be storing it on top of each other. Okay, 0x something, and you will be storing it on top of each other. Okay, and then you have positions like this. The stack is a position 0, stack position 0, stack position 1, and the stack position 2. Don't worry, if you don't get it right now, we'll get shortly into this. And here, when I will get a new instruction, here 0x, let's say something, some value I'm storing on the stack, this will get now it needs to be recomputed the position, so this will be now stack 0, stack 0, this will be 1, this will not 1, this will be 0, this will be 1, definitely, this will be 2, and this will be 3. Okay, so that's how this will be. Okay, with that said, just note here in this that the EVM is executing bytecode, and the instruction from a bytecode will be stored into the stack. Data, temporary data into memory, and the storage, persistent data. Okay. Let's continue. And now when we have here bytecode, let's take a look here on the instructions here. So instructions are executed byte by byte. This means, let's make it clear here. Okay, so I'll copy this one more time, and I will space out all of the bytes. Okay, so we'll make here some spaces. So between each byte, I will make a space here, space here. So we'll have a nice order here, and we can navigate very easily here. And we'll get into very difficult stuff very soon. Okay, but I hope I will clear it out for you, so you will understand it. Okay, so that's the instructions for EVM. When we are making transaction, this is code, part of the bytecode, which will be executed by EVM. Okay. All right, and what we need to now, we need to know what each instruction means. We can get meaning of the instructions from the yellow pages of Ethereum. So let's search here for Ethereum and the yellow pages. Yellow pages, and let's go here, GitHub. I will include this in the description, and look for instruction. Each of this is hexadecimal, so this will we need to just search here for 0x60. So let's search here for 0x60. Okay, and you can see it's a push instruction. This means push 1 byte into the stack. Place one byte item on stack. Okay, so this means push 1 byte into the stack. Okay, I will mark here stack, what we are storing in the stack. This will be stack. Okay, under here I will be writing what's in a stack. Okay, so push 1 byte, 60 means push 1 byte into the stack, and this byte means this second byte in the sequence. So 60, 80 means push 80 on the stack. So I am pushing 0x onto the stack. Okay, that's my first item into the stack. Okay, continue. 60, 40. Again, push 1 byte into the stack. So push 1 byte is 40. So let's push 40 into the stack. 0x40. Now we have instructions 52. Let's search for a 52 instruction. Okay, so 0x52. MS store, save word to memory. What this basically do, it will store the 80 into the 40 position of the memory. Okay, I will write here also memory. Okay, so this is happening in the EVM in the background, okay, when it's executing our code. So this means store in a memory, in the memory on position 0x40 store 0x80, and this instruction also will remove the items from the stack because they are already stored in a memory. So on the position of the memory 0x40 store 0x80, and I will be talking about this, what this means in the details when we will be talking about the memory. So basically what this means is a free memory pointer. So this 0x80 is the location where we can write now data. The free memory pointer pointing to this location. We can freely write into this location. So when we'll be writing some data in the memory, they will be written here in a 0x80 automatically. Okay, so that's the basically free memory pointer. So we are marking this location it's free to write there. Okay, that's usually you will see with almost every smart contract. That's what the Solidity does, and basically it's creating free memory pointer. That's the initialization of almost every smart contract. You will see this 0, 60, 80, 60, 40, and 52. You will almost see in every smart contract. Okay, but don't worry about this line if it's not clear. I will be talking in the memory section about this. Okay, now we have here 34 instructions. So what is a 34? Let's see, 0x34. Call value. Get deposited value by the instruction transaction responsible for its execution. So basically what does this do? It will get you value of the ether you are sending in the transaction. Okay, so basically here we have made a transaction. Go to transactions and a contract creation. This will get me when this transaction was sent. This will get me the value. Okay, so this instruction 0x34 will get me the value I'm sending when I was making the transaction. So basically we have here value 0. We were not sending any ether. Okay, so 0x00. This basically means 0 ether. I'm sending 0 ether. This will get me this value from input from the value we are sending here. Okay, so that's a 0 ether. Now we are on a 34. Now we are on the AD. Okay, so let's find here AD 0x80. That's a DAP1. This will duplicate the first item in the stack. So this will basically duplicate is 0. So this will duplicate it. So now we have 2 items, the same items because they are duplicated. That was the 80. Now we have a 15 transaction, 15 instruction. So 0x15. 0x15 is 0. this is just simply checking is 0. It's checking the first item in the stack, and it's checking if it's 0. If this first item, if it's 0, it will change it to the 1. Actually, it will pop it out, and it will pop the 1 on top of this, and we will push the 1 on top of the stack. Okay, so if the first item in the stack is 0, it will push the 1 on top of the stack. If it would be 0, it would keep 0 there. Okay, so it pushed 1 now. Okay, because 0 was there. Okay, so this is 0. Okay, that was 15. Now 60. We are pushing 0f now. Push 1 byte 0f. So we are pushing on the top of the stack 0x 0f. All right, so we have this, and then we have instruction 57. Okay, so let's go to 0x 57 jumpy. This means jump if. Okay, so this what basically do. It says here to jump on the location 0f if stack 1 is 1. Okay, I will write it down here. Okay, so to make it clear. So as I told you, this is stack 0. This is stack 1 and stack 2. And what is this saying? This jumping instruction 57. This 57 instruction. If position of the stack 1, if stack 1 is 0, is 1, which is this, stack 1 is 1, then jump to stack 0. To stack 0. The value that stack 0 is holding, right? So if stack 1 is 1, which is this, jump into the position of 0f. So we should jump somewhere here on this bytecode somewhere else on position 0f. But what is the 0f position? First, we need to transform it from a hexadecimal to decimal to understand it. But there is something in the background of EVM where it's keeping track of the instructions in a bytecode, and they are ordered from the 1 and higher. Okay, so the first instruction here will be 0. The second one will be 1. This is called also PC program counter, okay, which is keeping track of on which instructions we are currently on. Okay, so we are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll mark all of them, okay? 10, 11, 12, 13, 14, 15, 16. This lecture will be very long, guys. 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Okay? So program counter is telling me, not telling me program counter, but this instruction to jump on a 0f, on a stack 0 position. Okay, so I will check. I will go to transform hex to decimal. Okay, I will find out what is what is this instruction 0f. Yeah, what's the value of the hexadecimal to decimal? 15. So I should jump on 15. So here I should be. Okay, so now I should be here on a 5B. Okay, so I will jump here. So my counter here, program counter, will be now here on the 15th position. Okay, and also I will remove something from the stack. So now I'm here on this 5B. Remember here we jump here and we can check what's the 5B. 0x5b. That's a jump destination. Okay, correct. We jumped into the jump destination, so that was correct. 5b. Okay, and this jump destination instruction also will remove 2 items. This first number here is saying how many items to remove from the stack. The second one is saying how many items to add to the stack. Okay, so we should remove the 2 items from the stack. So we have jumped, and we are removing 2 items, so we have a 0 on the stack now. And now we are on a 5b. So now we're getting into the next instruction, which is a 50. Okay, so we are going to 0x50. Okay, and that's a pop. A remove item from a stack. Okay, so we are removing item from a stack. It's empty. Stack is empty now. Okay, so we are 50. Now we are pushing again some bytes. So 60, 45, so we are pushing 45 on the stack. 45. On the stack 80, meaning we are duplicating it. So duplicating 0x45, we have duplicated it. That was 80, and now 60. Okay, 80 was duplicating 61D. So we are pushing 1D on the top of the stack, 0x1D. Okay, and then we are pushing 0 on top of the stack, 60, 0. So we are pushing 0x00 on top of the stack. Now we are calling instruction 39, so 0x39. Okay, so 0x39, that's a code copy. Okay, that's the interesting one. 0x39. So we are going to code copy now, and code copy is saying, okay, let me see it here. The code copy. Oops, I would like to remove this. Okay, code copy is saying that we should use the memory offset to write to it. The first item is memory offset of code copy. So code copy, how should I write for you? Code copy, that's the instruction code copy, right? Code copy. So take the stack 0, stack 0 will be memory offset to write. Okay, stack 1 will be offset, bytecode offset to read from, this is stack 1, and stack 2 is the length to copy. Stack 2 is the length of the bytecode to copy. Length of bytecode to copy. Okay, so I'm saying here on the stack 0, I have a 0, 0, so there's a 0. So I will be writing in memory into location 0. Okay, and I will be getting offset of the bytecode from a position 1D, and the length of this will be 0x45. Okay, so let's find out what does it mean. The most important parameters are 1D here, so that's where we are starting copy from. So let's find out what's number is 1D, convert, 29. So 29, we should start copying from a 29th byte here. Okay, so when I will check it out here, I will select everything. You can see it's a 58. 58 divided by 2 is a 29. Okay, let's take a look on the entire bytecode. This is entire bytecode that we are working with. That's getting into the transaction. So 29th byte, it's here. Okay, so basically it's saying start copying from here, start copying from here. Okay, so that's what we are saying there. Okay, 0x1d is a 29, and that's an offset from which we should start copying of the bytecode. So this is 29 byte is here, where is my cursor. Okay, and that other value here, 0x45, is saying how many bytes we should copy. So 0x45, how many bytes we should copy? 69. Okay, so 69 bytes we should copy. Okay, so from here, let's select all of this, and you will notice it's a 138. 138 divided by 2 is a 69. This what I'm selecting here is a 69 bytes. So that's the code from this offset here, 29 byte. Length of this is a 69. What I should copy. So I'm copying this bytecode, and you can see this is exactly the bytecode we are deploying. So that instruction here is saying here, this code copy, this instruction 39, to select the code which we should copy to blockchain, to the network, right? And the offset where we should store it locally when we are executing, when the node is executing, where it should store it in the memory, okay, of the program. Okay, so basically it will copy the code. This code is code here, which we are going to deploy, and it will pop out 3 values from the stack. that's what we will do. So we have only 0x45. Our code is in a memory, okay? So we have in the memory, we have a code to copy. Code to copy. And it should be on the 0x00. Okay, the code to copy, and there should be our bytecode. Okay, so now we have the bytecode there, perfect. And the stack we have one item, 0x45, and we can continue. Okay, so next instruction is a push 0, 60, 0, 0. So this means we'll be pushing here 0. So 0x00. And then it's the instruction F3. Okay, let's search for instruction F3. Oh, that's a lot of talking. 0x F3. And that's a return. Halt execution, returning output data. So we should be returning our output data, which should be basically our bytecode, and we should pop out our two items here. Okay, so we have empty stack. Guys, one thing to note here is that this return output data, this instruction 0xF3, is taking the memory offset from the stack position 0. So this is the memory offset. Okay, it's looking into, so 0x00, so it's looking in the memory 0x00, and that's basically here is the length of our bytecode 0x45. So this is returning the data from a memory, so this is returning the data from the bytecode. Okay, so there's the offset from the memory, and there's the length, the bytes in the memory from this offset. Oh, I just want to say this. And now FE, so 0xFE, invalid. This designate invalid instruction, and this basically also marking the end of initialization code. When you usually see FE, this is marking the end of initialization code, right? So this is the entire code, and you have here FE, this is marking the end of initialization code, and here this deployed code starting from here. And F3 was to return, right? So F3 was return. Okay. And this will get you data from a memory, the output data from a memory. So this will be basically your entire bytecode, what you have copied. The code to copy you will return, and that's what's gonna be deployed to the Ethereum. Oh, that was lots of explanation now, guys. But I had to explain you how does it work. If you need to, you can rewatch the lecture. But as you could see, these instructions are executed one by one, and they are stored into the stacks, and they are definitely doing something with our smart contract. They are taking the portion of the smart contract, and also they are verifying some things. Okay, before this jumpy location, if you remember that we were jumping here, if we wouldn't jump, there are other instructions here in between the location we have jumped to. Remember, we have been jumping to some location here. And before here, there are instructions that they are checking if we are sending ether in the transaction. And if we would send here some ether, this would be, your transaction would be reverted. Okay, so some of this transaction here should be reverted. You should check if you are sending some ether in the transaction, and if you are sending, revert it. Because basically we are specifying in our contract that when we are deploying contract, we shouldn't send any ether. We can also check it if it's a revert somewhere. I don't remember revert instruction, but it's a 0xFD. So let's search here for FD. Do we have such an instruction? Yeah, here is a revert, you can see. So here, somewhere here, we would be checking if we are sending ether in the transaction. If so, we will revert the transaction. So the transaction would basically fail, and it wouldn't get into the blockchain. So it would be basically here, you would see fail if we would be sending such a transaction. All right, guys, I think now you need some time to process all of the informations about this. So I'm highly encouraging you to ask questions if you have any. About the memory and this stuff, we'll be talking in a separate lecture, because it requires, again, another half an hour lecture, even more. So guys, that's gonna be it from this one, and I hope to see you in the next lecture, guys. Cheers.